This is lesson 2. You have a graph that looks like this. Make sure you have printed the notes so that this makes sense to you. This is a graph of f of x. We're going to label some important parts on the x-axis. This is the x-axis. This endpoint we're going to call A, and this right endpoint we're going to call B. Then you've got some other kind of critical x values inside here. I'm going to drop down from that peak, and I'm going to call this C1. I'll drop down from this peak and call that C2, and finally I'll drop down from this peak and call that C3. And these are all critical x values because either we have a horizontal tangent, such as here we have a horizontal tangent, here we have a horizontal tangent, or we have a corner where the derivative doesn't exist. So these are critical x values, but the a and b are also critical x values because we have endpoints at those x values. Okay, so it's pretty clear to see from this function where we have relative or local max. So I'm going to say on AB, not including the endpoints, so AB, we're going to talk about where we have relative max and mins. There's a relative max at x equals C1. That's where we have a relative max. But we also have a relative max at x equals C3. See, here's a relative max. Here's a relative to small neighborhood, and that occurs at x equals C1, x equals to C3. We want to use calculus to describe why those are relative maximums. So we're going to say they have relative max at those points because f prime of x, the derivative, goes from positive, so it goes from positive to negative at x equals C1 and x equals C3. So we might want to say up here that f prime of x equals 0 at x equals C1 and x equals C2, that's horizontal tangents, and f prime of x does not exist at x equals C3. We have a corner. So that together with the fact that the derivative goes from positive to negative. So see, we have increasing nature here, so the derivative is positive tangents, and then we switch to negative, this yellow, it starts to decrease. So we had positive slope here, and then negative slope, and the derivative went from positive to negative, making it a max. The same occurred at the other point. Okay, and for the same reason, there is a relative min at x equals C2 because f prime of x goes from negative to positive at x equals C2. So now, when we consider the endpoints in play here, then we automatically know we have relative max or mins. So there are definitely relative extremes at x equals A and x equals B because they are endpoints. No matter what, if you have endpoints, they are automatically going to be a relative max or min. And specifically, we could see here that this is a relative min. So on some small neighborhood, this is the smallest value. And we can also see that this is a relative min because on a small neighborhood, it is the smallest value. Then we go to this term called absolute extreme. So absolute, global, universal. So that means what is the biggest value? A lot of people here will say C1 is the biggest value, but C1 is not the max, it's where the max occurs. So we have to be careful with that. So I'm going to say f of C1 is the absolute max, the absolute biggest, and f of C3 is the absolute minimum. And then there's finally this thing called the absolute extremes, the biggest extremes, using a test called the closed interval test. And I'm going to focus on that when we get to the example that uses the closed interval test. So for now, I'll just leave it like that. Okay, next we're going to look at intervals of increasing or decreasing. We're going to say that f is increasing on. Now, there's a small pill to swallow here as you accept this. F is increasing on the interval a to c1. The pill you're swallowing is that I'm using a bracket, so just bear with me here. But it's increasing on the interval a to c1 in union with the interval c2 to c3. See, we can see that the function is getting bigger on that interval because the derivative is greater than 0 on some open interval, a to c1 parentheses union c2 to c3. And then next we're going to talk about decreasing. So we're going to say f is decreasing. So see, the function is getting smaller here and also getting smaller here. F is decreasing on bracket c1 to c2 in union with c3 to b, because f prime of x is less than 0 on the interval c1 to c2 in union with c3 to b. Now, if you're like me, you're having a little bit of trouble thinking, why on earth would I use brackets for increasing and decreasing? And it's simply using definitions from the math book that says as long as it's continuous and differentiable, if the derivative is greater than 0 on the open interval, then we just by standard say that f is increasing on some closed interval. So it takes a little bit of a swallow to accept that, but we're going to be consistent with our textbook.